You gotta be always careful that just because it works for certain cases, that it's gonna be true for everything. Just like the example that we were talking about, right? The one that we use as a count example. For him, you know, I work with the n1 to 3 and they generate the prime. Doesn't mean that he's gonna generate for every numbers, because I can give a count example that it fails at 41st number. You see? Good. So it is important that we are able to prove this by induction, the dominoes. First brick goes down, surely, but then I need to say, I pick any number, any order, kth order, then I need to show the next one goes down. So first domino falls, that's the step number 1 for the induction. Step number 2, assuming the k1 goes down, so you assume that, right? You assume that, okay, I'm going to assume 100th one goes down. I'm going to assume the millionth one goes down. Then what do you need to show? You need to show that that implies the next one also goes down. Okay? So step number 2 is called the induction hypothesis. The third step is called the result to proof. Then for the induction, you actually have 3 steps, you see? Basic, induction hypothesis implies the result to prove. We're going to talk about that. And then the inductive conclusion. You got to talk about the inductive conclusion, meaning my statement will be true for all positive integers. Okay? We're going to talk about it in details by going over an example, but let's have a look. Continue. So dominoes, man. First one goes down. Any kth one goes down, I need to show the next one will go down as well. Basic step. And here, assuming the n equal to k true, again, is called the induction hypothesis. That implies the next one goes down, it's called the result to proof. It's called the result to proof. So let us have a look at the following cases. So for induction, you're going to have various fields of math that you're going to incorporate with it. So some books talk about the induction right after sequence and series and binomial expansion combination. But some books talk about the induction at the very end of their chapter because they want to incorporate everything together. You talk about the sequence and series, a combination, later on calculus, trigonometry, vector, etc. So induction can be applied everywhere, but we're going to talk about within what we have learned last week, sequence and series and combination. But for series, for the induction, we're going to use this following identity all the time. Suppose you have Sn plus 1, which talks about the series of a sum from the first term to who? N plus 1th term, right? So it's going to be, what is it? A1, A2, A3 goes up to who? An minus 1, An plus 1. That's what it means by the Sn plus 1. Okay? Then I'm going to go who? Sn, which is up to who? N many terms. That's what it is. Okay? So what I know here is Sn plus 1 can be described by the sum of who? Sn, right? On top of Sn, how much do I need to add to go to the Sn plus 1? The An plus 1 many term. Okay, so I got to add by An plus 1 many term here. So that identity we're going to use so many times with the induction with series. So please make a note of that, okay?